Okay, so today we're going to be working on this truss problem here. It's pretty simple. We see we've got a pin and a roller. These are 2 feet apart, and we are, of course, 2 feet going up this way. We've got joints A, B, and C. So which also gives us member AC, AB, and BC. So we're going to first solve for the external forces, and then we're going to solve for the internal forces to come up and get our answers for this particular problem. And we'll notice here we've got an applied force of 300 pounds right at the top of this particular truss. So first thing we got to do, though, is determine whether this truss is statically determinate or not. So if you remember, for static determinant, our formula there is 2J equals M plus R, where J stands for the joints, M stands for the members, and R stands for the reactionary forces. So here we've got 2, let's figure this out. We got 1, 2, 3 joints. So, and we've got 1, 2, 3 members plus the reactionary force. Now, a lot of people will sit here and say, well, with our reactionary forces, we know that a roller has 1 force, and that's going to be applied in that direction. And a pin has 2 forces, one going that way and the other one going that way. And then they count up the forces. Well, I got 1, 2, 3, 4 forces on there, and then they would put that in. Well, that we don't count the applied forces, so don't make that mistake. We count 1, 2, 3. We're only counting the reactionary forces. An applied force here causes reactionary forces. So we got 3 reactionary forces. Well, 2 times 3 is 6, and 3 plus 3 is 6. So the equation equals itself. So this is statically determinate, and we can go ahead and continue. So if these didn't work out, and if they were not equal, then we could say, well, it's not statically determinate, so I cannot solve this using my reactionary forces, external forces, and my method of joints. And I would stop right there. I wouldn't need to go on any further with that. So now we're going to, as we look at this, we're going to break this up, and I'm going to relabel these particular forces. So we've got the reactionary force here, and this is point A. So I'm going to label this as a reactionary force at joint A in the Y direction, and this is going to be a reactionary force at joint A in the X direction. Here, this is my reactionary force at joint B in the Y direction. And up here we see this 300 pounds. Well, that's really the applied force at C, so the force at C, which equals 300. And I'm kind of labeling this because I need you guys to start to look at these and consider these as variables, kind of setting up equations, because we're going to have to set up a lot of different equations as we go through. So now I've got my forces, they're labeled. So I'm going to make up a chart. So my forces in the X, here, we'll start with those. What are my forces in the X? Well, I got RA of X, RA of X, and of course that's going to the right, so which means it's going to be a positive to the right. Any other forces in the X? No, so that's it. So now let's see, what are my forces in the Y? Well, I've got RA of Y, that is going up. I've got RB of Y, that's going up. I also have force of C, which is going down. And we also know that this one is actually equal to 300 pounds, so we can put that right there. So any other, that is all of my forces at Y. All right. Now, I've also got to come up with, when we're talking about statics, we got forces in the x, we have forces in the y, and we also have moments. So we got to decide here. We're going to have a moment. Now, we could pick any of these joints, and we're going to have a moment going around them. So what we want to try to do is we want to try to pick the point that has the most forces off of them so that we can cancel those forces out. So which in this case is the moment at point A. So we're going to take the moment about point A. So our moments are about point A. Now remember, a moment equals force times distance, or FD. So I don't like to use this X because sometimes people get confused with that. So we could also say force times distance. This would mean it'd be applied or implied that this is force times distance. Or if you really want to spell this out, we can also break this up into force times distance with these brackets, and that also means the same thing. So be careful when you use an X as a multiplication sign on these when we got variables, because it's very easy to get confused and things mixed up. So I generally try to stay away from using X as a multiplication sign when I'm doing these type of problems. So let's go back and see. Now, if we pick pin A, notice I've got RA of X is my force. The distance is 0, so the moment there is 0. I can do RA of Y, the distance again is 0. So there's no moment there with RAX or RAY with those forces, because there's no distance. However, I do have a moment about B. So I'm going to have a moment about point B, or joint B, and I also have a moment about C up here. So and let's see what those are. Well, the moment about B is going to equal the force, which is RBY, times the distance back. This is a normal force, so we got to go perpendicular back. That's 2 feet times 2 feet. Now, we got the moment here. So, moment about C is force at C. There is an applied force there at C. And my distance. Well, how do I determine the distance to this pin? Well, we can just kind of bring this down here, and we notice that this is intersecting right in the middle. So our distance here is 1 foot. So we could sit here using variables. The force at C is 1 feet, but we know that force at C actually equals 300 pounds. So let's go ahead and replace that. 300 pounds times 1 foot is our moment around C. And we also have to maintain and take a look at the direction. So the moment at B, if this pin is here, as I'm pushing that way, we'll be moving that way, so we are clockwise, or counterclockwise in this case. Well, this is indeed counterclockwise, so we're going to make that notation. This moment is counterclockwise. Now, if I'm pushing down on here, this is going to want to go down here, and as it rotates about that pivot, now we're clockwise. So the moment on C is clockwise. And that's going to basically make some difference in our plus or minus. So anytime we're clockwise with the right hand rule, this is going to be a negative, and counterclockwise is going to be a positive. So we got to remember negative for clockwise, positive for counterclockwise as we go through. So now we're left with different variables that we can use. One of them we already know. We're going to have to solve for these remainder variables. So we've got 1, 2, 3, 4, 5, and 6 variables. One of them is already solved, so we're going to have to find a value for the other 5 variables. And we do that using our static equilibrium equation. So sum of the forces about x equals 0. Let's start with that one. So what are all of our forces here about x? Well, we come back to our tab here. We've got Ra of x is the only one, and that's to the right, so that's positive. Alright, well, nothing else there, so Ra of x is equal to 0. We can go right back over here and say equals 0 pounds. Nothing, no force is being applied there. Let's do the same thing with now the sum of Rf of y equals 0. So now we got to add all of these up. So now we've got R of AY, that's going up, so that's positive. R of AY plus R of BY, which is also going up, so that's positive. And then we've got the force at C, which is going down, so that makes this a minus 300 pounds. Okay. Now, I'm putting the minus 300 pounds here, but if I need to, if you're having problems, recognize that this is the same thing as the height at C. So, but I've already been given that, so I'm just putting that number in there. But if I needed the variable, it would just be my variable f of c. Alright, now doing a little bit of algebra here to solve this. We add 300 to both sides of the equation. So we add 300 pounds, and we get 300 pounds equals Ra of y plus Rb of y. That's it. We've got to stop there. We can't do anything else because we don't know what any of these other variables are. So next we're going to have to go to the sum of the moments. And let me move on down here. So the sum of the moments about A equal the moment about B plus the moment about C. Okay, and we've already determined that the moment about C is clockwise, so that's negative. So we'll come back in and we'll address that here in a few minutes. So now let's go ahead. Here we know, let's do some substitution. So this is of course going to equal 0. So 0 equals, we're substituting in the value here for MB, because we know MB equals RBY times 2 feet, that's positive, plus MC, and here we're going to substitute our value for MC, which we've already determined. It's a negative 300 times 1 is negative 300 foot-pounds, or pound-feet. I'm running out of little room, so bear with me. Alright, now we've got our left with RBY times 2 feet minus 300 pound-feet equals 0. Now we go back to our algebra. Add 300 pound-feet to both sides. We end up with 300 pound-feet equals RBY times 2 feet. Now we can take both sides of the equation and divide them by 2 feet. So RBY equals 300 pound-feet divided by 2 feet. The unit foot cancels off, and we are left with 300 divided by 2, or 150 pounds. Excuse me. So now I've got 150 pounds for RBY, and I can come up over here, RBY equals 150 pounds. I'm left, I don't know right now, RAY, so I got to look for an equation. Is there anything that I can see and find that's going to give me RAY if I plug RBY back in? Well, yeah, looking up here, our static equilibrium equation for the forces of the Y gave us 300 pounds equals RAY plus RBY. So let's use that one. 300 pounds equals RAY. We're going to substitute in plus RBY of 150 pounds. Now again, doing algebra, we subtract 150 pounds from both sides of the equation, and we find out that RAY equals 150 pounds. So there we have it. We have solved all of these using reactionary forces. We've gotten RBY here of 150 pounds. We've got RAY here, which is 150 pounds. We've got RAX equal to 0 pounds. And of course, we started out with 300 pounds over here. Everything has been solved, and we are good for the reaction forces. We're going to come back here in a few minutes, and we will then use that to determine our internal forces on each of these joints.